For this problem here on Mastering Physics, we have a velocity versus time graph showing an object moving along the x-axis, and we want to know the net force acting on it at various points in time. So our first point in time here is at 1 second, which is right here. So what I'm going to look at is I'm going to look at the motion of the object from 0 to 3 seconds. Actually, we have a constant acceleration during that period of time. And so I'm first going to find that acceleration, which simply equals the slope. So the change in y over the change in x. So I'm going to pick points here. I have this first point, 0, 0. Then I have this point here, 3, 12. And I'm going to use those points to find the slope. So my slope is going to be 12 minus 0 over 3 minus 0, or 4 meters per second squared. Net force is another way of saying sum of the forces. So that's just equal to mass times the acceleration. So my net force here is going to be my mass, which is 3.3, times my acceleration, which is 4. And so I get a net force here of 13.2 newtons. Rounding to 2 sig figs is just 13 newtons. Moving on to part B here, my same idea, my acceleration equals my slope, which at 4 seconds, we're thinking about our slope, and that is actually going to be 0. This entire segment here from 3 to 6 has a slope of 0. So I can say my acceleration is just 0, and therefore my net force must also be 0. So the answer to B is 0 newtons. And then for C, I'm going to find my acceleration once again, which is equal to my slope. I'm going to pick some new points here. So I have the point 6, 12, and the point 8, 0. And that's going to be my acceleration for this entire time from 6 to 8, okay, including that 7 seconds, which is what I really care about. So my slope there is going to be 0 minus 12 over 8 minus 6, or negative 6 meters per second squared. Solving for my force, I'm doing F equals ma once again. So my net force, or the sum of my forces, is going to be 3.3 times negative 6, which gives me a net force here of negative 19.8 newtons. Rounded to 2 sig figs, I'm just going to put it in as negative 20. I will keep it as a negative though, because that net force is going in the negative direction, which is what results in the negative slope and negative acceleration here. For this problem, I'm looking for the apparent weight of a person riding in an elevator, and there was a note above this problem that told us that apparent weight was the same thing as the normal force. Okay, those are synonyms because what you actually experience as weight is your normal force. When you feel heavy or you feel light, your actual force of gravity has not changed, but your normal force often has. So apparent weight is just another way of saying normal force. First thing I'm going to do here is draw a free body diagram for a person standing in an elevator, and we're thinking again about the forces on the person. So we have the normal force from the floor of the elevator, and we have the force of gravity acting on the person. And I can think about this, sum of the forces is equal to ma. So in our first situation, we're thinking about the normal force or apparent weight on Zach while the elevator is going down, but before it starts to brake. So before it starts to brake, we can assume it's traveling at a constant, and that means that our acceleration is 0. And so my F equals ma is going to be Fn minus Fg equals 0. That entire left side is going to go away. So my normal force is going to be equal to the force of gravity, which is just mg, right? Making that substitution for gravity because I know Fg always equals mg. And so I can plug in the mass that I have, which is 90 times 9.8, and I get a normal force here of 882 newtons. Rounded to 2 sig figs, I'm just going to put in a weight of 880 newtons. For the second part, I'm going to start with the same equation, sum of the forces. In both cases, we've been doing sum of the forces in the y. I'm going to have Fn minus Fg. But in this case, I am going to have an acceleration because I'm thinking about this situation while the elevator is braking. Now, I don't know the value right away of that acceleration, but I can set it up using my kinematics equation. So if I think about what I know here in terms of kinematics, I know my initial velocity is negative 12 because we're descending at 12 meters per second. We're coming to a stop, so my final velocity is 0. Don't know my acceleration, but I do know that that takes place over a period of time of 2.5 seconds. Using one of my kinematics equations, Vf equals Vi plus At, I can say 0 equals negative 12 plus A times 2.5. So 12 equals A times 2.5, which means my acceleration here is 4.8 meters per second squared. So I can use this acceleration now in my F equals ma equation. Going back real quick to my free body diagram, that acceleration is going to be going up, right, now that we're dealing with that second situation. The reason why it's going up is my elevator's going down, so it makes sense that my acceleration's going up, and the sign of my acceleration matches, right? I got a positive value for my acceleration. That indicates that it's going up. So I'm going to go ahead now and start work with my F equals ma equation. So I have Fn minus mg equals ma. I can fill in the values here that I know, so it's going to be Fn minus 90, which is my mass, times 9.8, is going to be equal to 90 times my acceleration, which is 4.8. So I can go ahead and solve here for my normal force. So I end up finding for my numbers that my normal force here is going to be equal to 1,341.8 newtons. Since we're rounding to 2 sig figs here, that's just going to be 1,300 newtons. But it should accept 1,340 or 1,342 even. Moving on to my next one, I have an astronaut sitting in a chair inside of a rocket on a launch pad here, and I want to know how much force this astronaut exerts on his chair in two different situations while he's at rest and also while he's accelerating up at 12 meters per second squared. So I'm going to start with my free body diagram here showing the forces acting on my astronaut. So what I'm going to have here is I'm going to have the force of gravity on him, of course, and I'm going to have the force from the chair, which I'm just going to call a normal force. In this first case, we're at rest, so our acceleration is 0, so I can set up my F equals ma in the y direction here. And so it's going to be Fn minus Fg equals 0, since we're not accelerating. So I can sub in mg for my force of gravity. And so I end up getting the normal force equals mg, so 63 times 9.8. which means my normal force here is equal to 617.4 newtons. So that's the force that the chair exerts up on the astronaut. Technically, it says how much force does the astronaut exert on his chair, but it's the same thing. This is a Newton's third law pair. So whatever this force is that the chair exerts up on the astronaut, that's what the astronaut ultimately exerts down on the chair. And so it's just 617 newtons, rounded to 2 sig figs would be 620 newtons. In the second situation, we have the same basic setup. The only difference here is that now we're accelerating up at 12 meters per second squared. So when I set up my F equals ma, it's going to be Fn minus Fg, but now it's not going to be equal to 0. It's going to be equal to that y acceleration of the astronaut. And so I'm going to plug in the things I know here. Once again, this is going to be mg. It's going to be equal to ma. So I have Fn minus 63 times 9.8. That's going to be equal to 63 times 12. I go ahead and solve for my normal force, and I get 1,373.4 newtons. Once again, we need to round to 2 sig figs, so 1,400 newtons would be the proper answer, rounded to 2 sig figs. For this problem, I have two people pulling a crate across the floor. two different forces acting on it, so I'm going to start, as I always do, with my free body diagram for this crate. So we have a normal force here. We have the force of gravity. We have two pushing forces, or pulling forces, whatever you want to call them. I'll call it FP1 and FP2. And we're going to have the force of friction going the opposite direction that it's being pulled. As always, I'm going to set up my F equals ma in the x and the y direction. So in the y direction, I have Fn minus Fg, and that's going to be equal to 0 because I don't have any vertical acceleration. So I have Fn minus mg. I can substitute that in for my force of gravity equals 0. So my normal force is simply equal to 280, my mass, times 9.8, which is g. So my normal force is 2,744 newtons. In the x direction, thinking about the forces that I have there, so I have Fp1 plus Fp2 minus the force of friction, and this is also going to be equal to 0, but for a different reason. The y acceleration was 0 because we're not accelerating up and down as we go across the floor. We're not even moving up and down. The x, we're moving at a constant speed, so that means that my acceleration is 0. So I can substitute in for some of these. I know my two pulling forces are 450 and 340. For that force of friction, I can make that substitution. That is mu k times my normal force. That's going to be equal to 0. So I end up getting here 790 minus mu k times the normal force that I solved for with my May, 2744, equals 0. And when I go ahead and solve for that coefficient of kinetic friction, I get 0.2879. Rounding to 2 sig figs, we get an answer here of 0.29. No units on this one because it's a coefficient of friction. Next one, we have an object sliding on a level floor. It slows and comes to a stop with a constant acceleration of magnitude 2.4 meters per second squared. We want to know the coefficient of kinetic friction. So we're going to start with our free body diagram here. It has a normal force going up, force of gravity going down, and it's sliding along. I'm going to say it's sliding along to the right. That's the direction of the velocity. So friction's going back to the left. Thinking about the sum of the forces in the y direction, we can say the normal force minus the force of gravity is equal to 0 because as it goes across the floor it's not accelerating. So the normal force simply is equal to mg because I substitute in for the force of gravity. In the x direction, we're going to have just the force of friction. I'll say negative ff because it's going to the left is going to be equal to m times my x acceleration, and I know my acceleration is going to the left, so I'm also going to make that negative, and it has a magnitude of negative 2.4 meters per second squared. So I can substitute in for ff, so I'm going to say negative mu k times my normal force equals m times negative 2.4. So negative mu k times mg, which was my normal force that I found over here, is equal to m times negative 2.4. My m's cancel out here, okay, and I can go ahead and solve for mu. So when I go ahead and solve for mu, dividing both sides by g, and we can actually make both of these positive, I get a mu value here of 0.244, which means my correct answer is just 0.24. Moving on to my next one, I have a 1 kilogram wooden block pressed against a wall, and it's being pushed with this 12 Newton force that's going up at an angle as shown. We want to know if the block's initially at rest, will it move up the wall, down the wall, or stay at rest? So we're thinking here about static friction, and we're given that coefficient of static friction, and that's ultimately going to help us determine whether or not the block will move. So we're going to start with our free body diagram. Okay, We have the force of gravity going down. That's the easy one. The normal force in this case is actually going to the right because here's my surface, that wall. And so that wall is going to push to the right on that box. So that's the direction of my normal force. And we have this force pushing at an angle. And I'm going to actually go ahead and draw the components of that. So there's going to be one component going to the left and one component going up. And there is my 30-degree angle. So, solving for those components, we want to do that before we set up our max and may. We're going to say this x component is going to be 12 cosine of 30 because it's the adjacent side. This y component is going to be 12 sine of 30. So there also is a force of friction, but we don't know which way that force of friction is going quite yet. We're going to have to figure out a few other things first. The one thing I do know is friction is either going to be going up or down because we're dealing with friction from a vertical wall. And so that frictional force is going to have to be parallel to that surface, which means it's either going up or it's going down. What I'm going to actually look for first is I'm going to actually look for my normal force because that's going to help me determine my force of friction. And as weird as this sounds, I'm actually going to use my max equation to find my normal force because that's the direction of the normal force in this case. So I can say Fn minus 12 cosine 30. Those are the only two forces in the x direction, and that's going to be equal to 0. And so my normal force, which is equal to 12 cosine 30, is simply 10.39 newtons. What I'm going to do now is I'm going to figure out my maximum force of friction. We're dealing with static friction here, so that as that weird force of friction is less than or equal to the coefficient times the normal force. So I'm going to solve for that maximum force of friction based off of my normal force that I just found. So that force of friction is going to be less than or equal to my coefficient, which is 0.5, times this 10.39 newtons. And so I get that my force of friction is going to be less than or equal to 5.2 newtons when I round it. So what I need to think about now is knowing that my force of friction can be up to 5.2 newtons, and it can act in either direction. It can act up or it can act down, but that's the most amount of friction I can possibly have. The question is that enough friction to keep this object at rest? So let's think about what forces we have vertically acting on the object. So my y forces. I have the y component of that pull, this 12 sine of 30, or 6 newtons going up. I have the force of gravity, which is going to be equal to mg, so 1 times 9.8, or just 9.8 newtons going down. So how much force do I need to keep it at rest? Well, friction can provide an additional 3.8 newtons of force going up, then this object will stay at rest. And it turns out that I have up to 5.2 newtons. So I basically need, in order to balance out my forces, I need 3.8 newtons of force going up. And friction can be up to 5.2. So in this case, friction will be enough to keep this at rest. And so this object is going to stay at rest. All right, so next question, we're dealing with a car accelerating, and we want to know what is the fastest amount of time that the car could accelerate from 0 to 80 miles per hour based off of some coefficients of friction. So I'm going to draw my free body diagram here, as I always do. For the car, we have our normal force, we have the force of gravity, and we have the force of friction. And friction actually is the force that makes cars move forward. It is the force that stops cars, but in the case of a car speeding up from rest, it's actually friction pushing forward on the car that makes it move forward. There's two ways I think about this. Number one, when the tires are spinning, they're rotating in such a way that they're pushing backwards on the road, okay? And we know from Newton's third law that if the tires push back on the road is going to push forward on the tires and therefore push forward on the car. The other thing to think about is when it's really icy out, and you slam on the gas, a lot of times what will happen is your tires will just spin in place. What is the thing that you've removed that no longer makes you accelerate? And the thing that you've removed is the friction. That's what happens when it's icy out. There's not a lot of friction, and it's difficult to accelerate forward because you don't have a high coefficient of friction, and so you can't have a very big force of friction. So that force of friction moving forward is actually what propels my car forward. So my acceleration there is going forward like that. I'm going to set up my F equals ma, starting with the y. So I have Fn minus Fg equals 0. Subbing in for f of g and solving for my normal force, I get that f of n is simply mg. In the x direction, sum of the forces in the x equal max. I just have this force of friction, and that's going to be equal to the mass of the car times its x acceleration. I'm going to now sub in for the force of friction, and in this case we're going to be dealing with static friction. When we're speeding up, ideally our tires are not sliding or skidding with respect to the road. So even though the car itself is moving, this is still a static friction case because the tires are not sliding along the road. The other thing is too, even if the tires are sliding, that's not helping us accelerate at the greatest possible rate, because we can see that our static friction coefficient is greater than our coefficient of kinetic friction. So we're dealing with static friction, and we're dealing with a situation where the static friction is at a maximum. So even though our equation for static is that the force of friction is less than or equal to mu times the normal force, in this case it's just equal because we have a maximum force of static friction. So I'm going to say that the force of friction is simply mu s times my normal force. That's equal to m times my x acceleration. I'm going to plug in for my normal force using what I just found with my y. So mu mg equals m times my x acceleration. My m's cancel out here, and I'm just left with mu, which is 1, times g, 9.8, equals my acceleration. So my maximum acceleration that the car can have is 9.8 meters per second squared. And as you can see from the problem, that's really the limiting factor in terms of cars speeding up. All right, the acceleration really depends on the tires and the coefficient of friction, not necessarily the engine. You get to a point where the engine's powerful enough, but it doesn't matter if you don't have the friction to get the grip between the tires and the road to actually accelerate forward. So let's go ahead and actually find this final answer, which is the time. That's what we're ultimately looking for in order for the car to speed up. So I'm going to set up my kinematics equation here to solve for that time. My initial velocity is 0 since I'm starting from rest. My final is 80, but it's in units of miles per hour, so I need to convert that. 1 mile is 1,609 meters. 1 hour is 3,600 seconds. And so I end up getting a final answer here of 35.8 meters per second is my final velocity. And my acceleration is 9.8 meters per second squared. That's what I just found, so I can solve for my time. Here I'm going to use the VF equals VI plus AT equation. So I have 35.8 as my final velocity, equals 0 plus 9.8 times my time. I solve for my time here, and I get a time of 3.65 seconds. Rounded to 2 sig figs, I have 3.7 seconds. Moving on to my next one, I'm given the coefficient of friction between a box and a desktop, and we want to know what is the force of friction when a pushing force of 15 newtons is applied to the box. For my free body diagram, I have my normal force acting up, my force of gravity acting down, I have some pushing force, and I have the force of friction. In the y direction, sum of the forces in the y equals m times ay. I have Fn minus Fg, and we're not accelerating vertically here, so that's equal to 0. So my normal force is simply equal to mg. If I plug in my mass, that's going to be 3 times 9.8, or 29.2 0.4 newtons. Now we think about our forces in the x. We want to know what is the force of friction in this case. So in the x direction, we have Fp minus Ff equals max. But we need to answer an important question, and that is 15 newtons enough to make this box move? Are we dealing with a static friction case or a kinetic friction case? Because that's going to change how we go about finding our force of friction. So in order to determine whether or not it's enough to make the box move, I'm going to solve for my maximum force of static friction. I know that static friction is going to be less than or equal to mu times my normal force. So my maximum force of static friction is going to be less than or equal to 0.4 times that 29.4 normal force that I just solved for. So I find that my force of friction here is going to be less than or equal to 11.76 newtons. So that means the box will move because my pushing force is greater than my maximum force of static friction. So we're dealing with a kinetic case here, and so I just need to find my force of kinetic friction, and that's just going to be Ff is equal to mu k times my normal force. I know that my coefficient of friction is 0.3, my normal force is 29.4, and so my force of friction in this situation is 8.82 newtons, so 8.8 is my answer. For my next problem, I have two objects on an incline, two boxes on an incline at rest, and we want to know the tension in the strings based off of what we know about the boxes. So I'm going to start with a free body diagram on each box. So starting with box 1, I'm going to have the force of gravity acting on that, and I'm going to have a normal force. I'm also going to have the force of tension from rope 1, which I'll call Ft1. On box 2, I'm going to have the force of gravity. I'm going to have my normal force. I'm going to have the force of tension on box from rope 2 pulling up, and I'm going to have the force of tension from rope 1 pulling down. And these two forces here, they're really, I know it's through a rope, but they're the forces that box 1 and box 2 exert on each other, so they are equal and opposite. That's a third law pair. In both cases, since we're dealing with an incline, we tilt our axis, and that means we need to do the components of our force of gravity. So my y component is going to be Fg cosine of 20 for both of them, and my x component is going to be Fg sine of 20. I want to determine the tension in rope 1, so I'm going to start with box M1 to do that, simply because there's less forces, and here I really only care about my F equals ma in the x direction because that is the direction of rope 1, and our incline is frictionless, so I don't even need to find my normal force here to find my force of friction. So force-wise, I'm going to have Ft1 minus Fg sine of 20, and that's equal to 0 because the boxes are at rest on the incline, so there's no acceleration for either one. So I can substitute in some of the things I know. Solving for Ft1, I know that Fg is mg, so it's mg sine of 20 equals 0. So Ft1 equals my mass, which is 3 times 9.8 times sine of 20. Solving for that, I find that Ft1 is equal to 10.06 newtons. Answering that to 2 sig figs, and we just get an answer of 10 newtons. Moving on to part B, I'm going to think about the forces acting on the second block in order to solve for the tension in rope 2. So I have some of the forces in the x equals max once again, and that's going to be Ft2 minus Ft1 minus Fg sine of 20, all acting on object 2, is equal to 0. And so I end up getting ft2 minus 10, which was ft1. Remember, these two are equal because it's a third law pair. And that's going to be minus mg sine of 20 for the block 2, and that's equal to 0. So ft2 minus 10 minus 1 times 9.8 times sine of 20 equals 0. So I end up finding that ft2 is equal to 13.4 newtons. When I round to 2 sig figs for my answer, it's just 13 newtons. For this one, I want to find the minimum downward force that we need to apply to this box to keep it at rest when it's pulled to the right with a force of 125 newtons. Starting with my free body diagram here, I have the normal force going up. We have the force of gravity going down. We also have this pushing force, F, going down. It's being pulled to the right with 125 newtons of force, as shown in the diagram, and we have a force of friction going back to the left. For my May in the y direction, I'm going to have Fn minus F minus Fg, and that's going to be equal to 0 because there's no vertical acceleration. And in the x direction, I'm going to have that pulling force minus the force of friction also equal to 0 because we want to keep the object from slipping. That is the key here, to keep it from slipping, keep it from moving. Since we are dealing with a situation where we want to keep it from moving, that is going to be a static situation. So in that case, force of friction is less than or equal to mu times my normal force. And since it's a situation where it's the minimum downward force, that means we're going to need to use all of my force of friction. So it's not a less than or equals to in this case, it's simply equals to. So I can say, working with my x equation, Fp, which is 125, minus mu s times my normal force must be equal to 0. So 125 is equal to my static coefficient of friction, 0.1 times my normal force. That means that my normal force is going to be equal to 403 newtons. And now I can actually go backwards now and use that in my y. It's kind of the opposite of what we typically do, but that's okay. So I'm going to say 403, which is my normal force, minus F, minus Fg, which in this case is going to be mg, has to be equal to 0. So 403 minus F minus 30 times 9.8 is going to be equal to 0. And so when I solve for F from that equation, I find that that force is equal to 109 newtons. We're expressing our answer to 2 sig figs, so that would be just 110 newtons. Next problem here, we have a flatbed truck carrying a 20 kilogram crate up a sloping road, and we're given the coefficient of static friction between the truck and the bed, as well as the coefficient of kinetic friction. And we want to know the maximum angle that the truck can climb up at a constant speed if the crate is going to stay in place. So we're going to start with our free body diagram, and our truck beds are going to be sloped at some angle here, theta, as it's climbing up this hill, right? If we're imagining, and that's a very poorly drawn truck, but you get the right idea here. Our truck going up the hill, it's going to look something like that. So it's going to be sloped at some angle. So here's our box or crate on the truck, and the forces we're going to have the force of gravity going down, we're going to have the normal force going up, and the force preventing it from sliding is going to be the force of friction. As we always do with these ones on inclines, we tilt our axis and we break the force of gravity into the x and y components. So Fg cosine theta and Fg sine of theta. Setting up my max and May in the y direction, I'm going to have my normal force minus FG cosine of theta is equal to 0 because we're not accelerating perpendicular to that incline, to that slope. So my normal force is equal to mg, substituting in for f of g, times cosine of theta, that unknown angle. So I can say my normal force is going to be 20 times 9.8 times cosine of theta, or if I multiply that out, that gives me a normal force here of 196 cosine of theta. In the y direction, in the x direction, setting up my forces as well. I know my acceleration is 0, and so the force is ff minus fg sine of theta must balance out and add up to 0. And so I can make a few substitutions here. First of all, I can substitute in mg for f of g, as I always do. The other substitution I can make is I can say ff, we're dealing with static friction here since we're not sliding, is less than or equal to mu times my normal force. And since we're looking for the maximum angle, that tells me that force of friction will be at a maximum here, so I can say that they're just equal. And therefore I can substitute in mu s times my normal force for the force of friction. And that needs to add up to 0. So we plug in for the normal force I just got, 196 cosine of theta, minus 30 times 9.8, my mass times g, times sine of theta equals 0. When I multiply that out and move it to the other side, I get mu s times 196 cosine of theta equals 196 sine of theta. So those 196's actually cancel out, and I never really needed to put them in the first place, but it's obviously okay if you do. And so what I'm left with now is mu s times cosine of theta equals sine of theta. And here's where that trig identity comes in that's going to be really important. And that identity is that sine of theta over cosine of theta is equal to tangent of theta. So we're going to apply that to help us solve this problem. And here's why that identity is so important, is when you have a situation where you don't know the angle and you have both a sine of theta and a cosine of theta term, you somehow need to get theta by itself. And you can't just divide by sine or divide by cosine, right? You need to somehow combine them and their functions, so it's a little bit tricky to do that. And so this identity really comes in handy because what we can do is, I know that if I can somehow divide sine of theta by cosine of theta, I'm going to be left with a tangent of theta, and I'm going to go from 2 thetas down to 1. So I divide both sides by cosine of theta. On the one side, the cosines cancel each other out, and so I'm left with mu s is equal to sine over cosine, which is just tangent. Okay, and I can substitute in my coefficient of static friction, which I know is 0.40, and that's going to be equal to tangent of the angle. So the inverse tangent of 0.40 is equal to my angle. So I find here that my angle is going to be 21.8 degrees. So that would be rounded to 22, so there's my answer.